Welcome back everyone to this video on 5 binomial identities in 5 minutes. So we're going to take a look here at 5 binomial identities that all relate to Pascal's triangle in some way. The first one has to do with the sum of the rows of Pascal's triangle. And I claim that the sum of every row of Pascal's triangle is going to be a power of 2. So the 0th row at the top here has a sum of 2 to the 0th power, or 1. The sum of the first row has a sum of 2 to the first power, or 2. The sum of the second row has a sum of 4, or 2 to the second power. The sum of the third row has a sum of 8, or 2 to the third power. And the sum of the fourth row has a sum of 16, or 2 to the fourth power. So, in general, I claim that the sum of the nth row has a sum of 2 to the nth power. And to prove this, we're going to use the binomial theorem. So recall that the binomial theorem states that x plus y to the nth power can all be written in terms of combinations of n choose k. And then we have x to the n minus k times y to the k there as well. So if we let x equal y equal to 1 in the binomial theorem, then we're just going to get 1 plus 1 to the nth power is equal to a bunch of sums of n choose k all times 1, which is just equal to the sum of the nth row of Pascal's triangle, which is also equal to 2 to the n. So therefore, we've proven our desired identity. So we're now going to look at the alternating sum of rows of Pascal's triangle. And we see that for all of the rows after the 0th row, so for the very first row we have here, we have an alternating sum of 1 minus 1 or 0. For this one, we have 1 minus 2 plus 1 is equal to 0. For this one, we have 1 minus 3 plus 3 minus 1 equals 0. And for this one, we have 1 minus 4 plus 6 minus 4 plus 1. So all the positives here sum up to 1 plus 6 plus 1 equals 8. And all the negatives sum up to negative 4 minus 4 is equal to 8 as well. So the alternating sum is always equal to 0. And I claim that in general, if we do the alternating sum of the nth row of Pascal's triangle after the first row, we always get 0. And to prove this, we're just going to set x equal to 1 and y equal to negative 1 in the binomial theorem, and we're going to get 1 minus 1 to the nth power is equal to the sum of n choose k times 1 to the n minus k times negative 1 to the k, which is just going to be equal to, because 1 to the n minus k is equal to 1, n choose 0 minus n choose 1 plus n choose 2, and so forth. And as a corollary, can you use this to prove that there is the same number of odd and even subsets of a finite set, as a fun exercise to try later on? And leave your answers in the comments below, please. And so that will be equal to 0 as well, because 1 minus 1 to the nth power is equal to 0. So the next identity has to do with the every other term sum. So notice that if we sum up every other term, let's say in the third row, we get 1 plus 1 is 2. In the third row, we're going to get 1 plus 3 is 4. In the fourth row, we get 1 plus 6 plus 1 is equal to 8, which is just always going to be 2 to the row number minus 1. And we claim that this holds in general. And to do this, we see that if we add the previous two identities, which we've shown here, well, all of the odd terms are just going to cancel out. So n choose 1 terms cancel out, n choose 3 terms cancel out, and so forth. So this gives us 2 times all of the even ones, so n choose 0, n choose 2, n choose 4, is equal to 2 to the nth power. But if we divide by 2, we get the desired identity, that every other row of Pascal's triangle sums to 2 to the n minus 1. Next up, we're going to look at this fun identity here, which involves multiplying each of the binomial coefficients by corresponding powers of 2. And we see that if we do this, we get a sum of 3 to the nth power. So as a question to you, what do you think x and y should be here in the binomial theorem? And please comment with your answers below as well. I'll give you a minute to think about that. And we see that when x is equal to 1 and y is equal to 2 in the binomial theorem, we have 1 plus 2 to the nth power is equal to the sum here of n choose k times 1 times 2 to the k, which is just equal to n choose 0 plus 2 times n choose 1 plus 2 squared times n choose 2, and so forth, which is equal to 3 to the n. And finally, I claim that if I multiply all the terms in Pascal's triangle, except for n choose 0, by the corresponding coefficient, so 2 times n choose 2, 3 times n choose 3, and in general n times n choose n, we're going to get n times 2 to the n minus 1. And to prove this, notice that each term in our sum is equivalent to k times n choose k, which is equal to k times n factorial divided by k factorial times n minus k factorial. The k and k factorial factor out there, and we get n factorial divided by k minus 1 factorial, where if we factor out an n in the numerator here, we just get n times n minus 1 choose k minus 1. So therefore, we can rewrite the summation as shown here, which is just going to be, we have a factor of n times all the terms, times n minus 1 choose 0, plus n minus 1 choose 1, and so forth, which is just going to be equal to n times 2 to the n minus 1, which proves our desired result. Thanks so much for watching.